I welcome you all in this new session. I am Dr. Muhammad Ehtishamul Haq, and we are going to continue with our absorption refrigeration system. We have discussed part of it in the previous lecture. This is week 5, lecture number 1. So I'm going to start again on this cycle on the absorption refrigeration cycle. We are going to discuss the working principle of it, its application, and its advantages. So let's get started, and we'll see some examples how to do the calculation for this cycle. So these are the 4 components that we use in vapor absorption refrigeration cycle. It's a condenser and evaporator, same as we had in vapor compression cycle, but compressor has been replaced with absorber and generator, and also with a pump. So these 3 items are replacing the compressor that we had in the a simple vapor compression refrigeration cycle. So the basic absorption cycle, this is the basic refrigeration cycle. This diagram here with 4 of its main components: a generator, a condenser, an evaporator, and an absorber, and then it has a pump and a throttling valve. So it is also a 2-pressure system, same as before. Low pressure is in the evaporator and the absorber, and high pressure is in the condenser and generator. Low pressure vapor from the evaporator is absorbed by the liquid solution in the absorber. So the absorber, which has lithium bromide salt in it, it has an affinity for the water vapor. So low pressure vapor from the evaporator will be absorbed by the absorber. So hence the cooling will be produced in the evaporator. If this absorption process were executed adiabatically, the temperature of the solution would rise, and eventually the absorption of the vapor would cease. So if it can go on for a certain time, if there is it's an adiabatic process. So if no heat is being released from the absorber, so then it will be an adiabatic process. In this case, it will go up to a certain period of time, then this solution will become saturated, and there will be no more cooling process. So for that purpose, the absorber has to reject some heat. It will be rejecting heat to the ambient, you can say that, or you can have a cold water circulating into the absorber. It will absorb some of the heat, so the process can continue. To perpetuate the absorption process, the absorber is cooled by water or air that ultimately rejects heat to atmosphere. So to continue this thing, we need to eject the heat from the absorber. The pump receives low pressure liquid from the absorber, elevates the pressure of the liquid, and delivers it to the generator. So from the absorber, low pressure and you can say low temperature liquid will be supplied to the pump, and it will pump it to the high pressure generator here. So this will be, if you look at the concentration of lithium bromide, so here, because this lithium bromide has been absorbing water vapor from the evaporator, so its concentration will be low, and this low concentration solution will be pumped to the generator. In the generator, heat from a high temperature source drives off the vapor that had been absorbed by the solution. In the generator, we are supplying that our low heat from solar energy or from any other waste heat. We supply that low heat to the generator. As a result of that, the water will get separated from the lithium bromide solution. So the water vapor will be going into the condenser and the high concentration solution, because the vapor has gone, because the solvent has left it. So the high concentration solution will be transferred through this expansion valve to the absorber. Okay, so this process will go on like that. The liquid solution returns to the absorber through a throttling valve, whose purpose is to provide a pressure drop to maintain the pressure difference between the generator and the absorber. So this throttling valve is basically for to maintain the pressure difference between the generator and the absorber. So the high concentration solution from generator will come back to the absorber. So now the absorber will have high concentration, so it will be able to absorb more water vapor, water vapor from the evaporator. And from here the water vapor from the condenser will go to the evaporator. Let's go back there. The water vapor from the high pressure water vapor go to the condenser. It will cool off. It will give heat to the atmosphere and become liquid. That will go to the expansion valve, and again after the expansion valve it will expand, become vapor. This vapor will go into the evaporator. So that is the cycle which goes on, keeps on going, the basic absorption cycle. Okay, so as you can see, low temperature heat is absorbed in the evaporator and high temperature heat is given to the generator. So these two we are supplying heat. Similarly, absorber is rejecting heat because this absorption of the water into the lithium bromide is an exothermic reaction, so it will give up some of the heat. So low temperature heat is being rejected into the environment here, and condenser will reject the high temperature heat from here. So if you compare it with the vapor compression refrigeration cycle, you can say that you have two processes which are similar to condenser. One is the condenser process where the heat is being given out into the atmosphere, and this is the same condenser process as we had in the vapor compression refrigeration system. But this is for the refrigerant, and this one is for the solution. Here also, it is also the absorber is also acting as a you can say that it is similar to a condenser, but this is condenser for the solution. So the heat will be rejected into the absorber also absorber also. So these two are heat rejecting, and then high temperature heat is absorbed in the generator and low temperature heat is absorbed in the evaporator. So that is the process, that is the simple process that goes on in a vapor absorption cycle. So let's move on. Let's look at some further detail. The pattern for the flow of heat to and from the four heat exchange components in the absorption cycle is that high temperature heat enters the generator, while low temperature heat from the substance being refrigerated enters the evaporator. The heat rejection from the cycle occurs at absorber and condenser. So energy absorption is occurring at the generator and the evaporator, while heat rejection or energy rejection occurs at condenser and absorber. The heat rejection from the cycle occurs at the absorber and the condenser at temperature such that the heat can be rejected to the atmosphere. So that completes the entire vapor absorption refrigeration cycle. I hope you understand. If there is any question, you can ask me during your live session. Now the application of absorption refrigeration system. The absorption refrigeration systems are much more expensive than the vapor compression refrigeration system because these are large systems. As I have mentioned it before, that we don't make a vapor absorption refrigeration system for like 4 tons or 2 tons or 1 ton. This is normally made for a high refrigerating capacity for like 10 tons, 20 tons, 40 tons, 50 tons, and use it in large industrial building or commercial building. So that's why it is expensive. They are more complex and occupy more space. They are much less efficient, thus requiring much large cooling towers to reject the waste heat. And they are more difficult to service since they are less common. Because they are less common, the service technicians available are not that many. And they are bulkier, they are heavier, their COP is less than 1. Therefore, absorption refrigeration system should be considered only when the unit cost of thermal energy is low and is projected to remain low relative to electricity. Absorption refrigeration systems are primarily used in large commercial and industrial installation. So if you have a waste heat, some kind of waste heat available through your gas generator, gas turbine, or from your steam turbine, from anywhere that you are wasting heat, or a diesel engine that you are using in your company, in your factory, then that waste heat, if it is available, then vapor absorption system will be a good idea. Normally in thermal power stations also this option is good. Or if you have a good solar system installed, then if solar heat is easily available, then this will be a good viable thing. You need to have cheap thermal energy available for a long period of time, at least for like 10-15 years, because the cost of the vapor absorption plant is large. So unless you have the low cost energy heat available for 10 years or 15 years time period, then installing this one will be not a viable idea. You have to have a low cost heat available for 15 years or maybe more. Then this idea will be viable. Even though it's an ongoing research on it going on, and how to make it cheaper and smaller is going on, but currently the situation is what I'm trying to mention you here. The operation of absorption refrigeration system is based on heat transfer from an external source. Therefore, they are described as heat-driven system. The electrical energy required by the pump is very small. So the main energy used is in the generator, and generator is not using your electrical energy, it is using the heat. So it is called heat-driven system. Economically attractive when source of inexpensive thermal energy at a temperature of 100 to 200 degree is available. Normally a gas turbine or a steam engine normally gives out energy at 350-400 degree, maybe 600 degree centigrade. So but the minimum requirement here that you have 100 to 200 degree temperature energy available, then this will be a economical option. Possible energy sources can be geothermal energy, solar energy, waste heat, and natural gas if available at relatively low price. These systems involve absorption of a refrigerant by a transport medium. So the transport medium here is the water which is circulating into it. So that is the refrigerant, okay, the transport medium will be the lithium bromide, and lithium bromide, and refrigerant is water. The COP of absorption refrigeration system is defined as COP is desired output, required input. So the desired output is the same as rate of refrigeration required, and the input will be the heat supplied to the generator plus the rate of work supplied to the pump. So there is two types of energy which is required. One is going to the generator, which is the heat, and electrical energy to the pump. So these are the two components. In vapor absorption, we have only one, electrical energy supplied to the compressor, but here it's two form. But compared to the energy supplied to the generator, the energy required by the pump is very small. So normally we ignore it. So heat absorbed in the evaporator divided by the heat supplied into the generator. QL upon QGen is the COP of the absorption cycle. COP of an absorption cycle is usually less than 1 compared to 3 and above for the vapor compression cycle. So vapor compression cycle generally has higher COP as compared to the vapor absorption cycle. But this vapor absorption cycle is only useful when you have waste heat available in larger quantity and for a longer period. The equilibrium, okay, so that's about the COP of it. Now we want to go on how to do the calculation, how to find out the enthalpy of this cycle. As we've been doing it, we need to find out enthalpy at 4 corners of the cycle. So here also we need to find out enthalpy for this system. So how to find the enthalpy? Enthalpy, if this is a lithium bromide and water system, then the condenser and the evaporator will have water vapor, saturated water, okay, saturated water vapor in it. So for these two we can use our normal steam table. we'll try to find out what is the enthalpy before the condenser, so at this point, and after the condenser at this point. And similarly, what is the enthalpy before the evaporator, which will be the same as what we find out here, and after the evaporator here. So at these 3 points we need to find out what is the enthalpy of water vapor. That we can find out with the steam table. Now the problem is with this solution. The solution is in the absorber and in the generator. How to find out enthalpy in the absorber and in the generator? For that we use two graphs. One of them we call it PXT graph, pressure, concentration, X for concentration, and temperature graph. The other one we call it HXT graph, enthalpy, concentration, and temperature graph. So with the help of these two graphs we can find out what is the enthalpy of the solution. So I want to explain you that process here. So okay, here you go. Vapor absorption cycle calculation. How to do the calculation? Calculation basically will depend on how first find out the enthalpies, and then we can add, subtract the enthalpies to find out the QL and the QGen. Okay, Q generated. The calculation of vapor absorption cycle involves two property charts and a table for the saturated water enthalpy. So saturated water, we will be using the same steam table for the saturated water, and for solution we will be using two property charts. Those two charts I already mentioned. One is the PXT, the other one is the HXT. So we are going to look into that one and how to find out enthalpy of the solution using those two charts. So it says the equilibrium chart of aqueous lithium bromide solution. This is figure number 17-5 in the Stoker. I will show you this figure. Okay, the equilibrium chart. So equilibrium chart has been developed for the lithium bromide solution, aqueous lithium bromide solution, water solution. So that is a chart which tells you what will be the concentration if concentration of lithium bromide in water if the pressure of the solution is this much and the temperature is this much. So that first graph will tell you that with the temperature and the pressure, it will tell you what will be the concentration of the lithium bromide solution, and you will see it because these charts has been made in equilibrium condition when both containers are in equilibrium. We consider one container having solute, the other container having solvent, and when they are open, so the lithium bromide will absorb water vapor until it becomes saturated, and when it becomes saturated, the pressure in lithium bromide and pressure in water vessel, they are both same. Lithium bromide solution and water vapor, they will be same. That is the equilibrium. At that point the graphs or charts has been made. The second one is the enthalpy concentration diagram for lithium bromide water solution, 17-8. So this is enthalpy concentration diagram. With the help of this, once we know what is the concentration from part A, we can use that concentration to find out the enthalpy in part B. So figure 17-8. With the known solution and refrigerant temperature, the corresponding refrigerant concentration percentage in the mixture can be obtained from the equilibrium chart for aqueous lithium bromide solution. Is a temperature pressure diagram. With the known solution and refrigerant temperatures, the corresponding refrigerant concentration in the mixture can be obtained from the equilibrium chart for the aqueous lithium bromide solutions. So if we know what is the temperature of the solution and what is the pressure of the solution, we can tell what is the concentration of that solution. Temperature and pressure if we know. So the temperature you can measure, pressure because both of these tanks, the lithium bromide and water, are connected to each other. So at a given temperature of water, you will always know what will be the saturated pressure. So that same saturated pressure will be in the lithium bromide solution tank. So we will know the pressure in that fashion because we know this the saturation pressure of the water. So the other tank will have the same pressure, and we can measure the temperature. If we know these two things, then we can determine, with using the chart, we can determine what is the percentage of lithium bromide in that solution. Then with the known refrigeration concentration and solution temperature. Okay, this is the part B. Then with the known refrigeration concentration and the solution temperature, we can get the enthalpy of the solution from the concentration diagram of the lithium bromide water solution. Okay, so first we will know what is the solution's temperature and what is the pressure of the solution. Okay, once we know it, we can find out what is the concentration. Once we know the concentration and temperature of the solution, then we can find out what is the enthalpy value of it. It's fairly easy. Once I show you, you will understand. The enthalpy of the refrigerant, which is water in case, can be obtained from the table of saturated water. So the enthalpy of the water we can easily find out from the saturation table. So these two steps, the A and B step, or the A, this point and this point, these are for the solution, and for the refrigerant, which is water, it is part C. Okay, A and B are for the solution, C is for the water. So moving on. So this is the tank that I keep telling you. Okay, the equilibrium chart of aqueous lithium bromide solution. So on one tank we have water, and on the other tank we have lithium bromide. So if we connect these two, okay, so then, because the lithium bromide has an affinity for water vapor, so it will start absorbing water vapor. So water vapor from here will start escaping and coming here, and the process will keep on going till this is saturated. And the saturation occurs when the vapor pressure here and the vapor pressure of water here are the same. Then it will be in equilibrium. Then no more water vapor can pass from here to lithium bromide solution tank. So this is the chart which is made. So at 40 degrees centigrade, the vapor, if you look up this steam table, what is the saturation pressure at 40 degrees centigrade of water? So you will see it is 7.38 kilopascal. So this process will go on till the other tank has the same 7.38 pressure. So we know the pressure, temperature we can measure. So what is the concentration? Concentration should be 59%, because we measured the temperature of the lithium bromide water solution, it was 80 degree. So it will be 59 degree. We can have same vapor pressure for another temperature solution and concentration. When it is in equilibrium, it is possible to have another concentration of lithium bromide with a different temperature, and then it will be again in concentration. So one vapor pressure can have multiple solution temperature and concentration at the same vapor pressure. So that is why we call it equilibrium aqueous lithium bromide solution. Lithium bromide is a solid salt crystal. In the presence of the water vapor, it will absorb the vapor and become a liquid solution. This is what we call that the lithium bromide has an affinity for water, so it will try to absorb water. The liquid solution exerts a water vapor pressure that is a function of the solution temperature and the concentration of the solution. Because those two tanks are connected with each other, so at certain point they must have the same pressure in both of them. Till they have the same pressure, the process will go on. Keep on going. Otherwise, when equilibrium is established, then there will be no more transfer of water vapor from this tank to the other tank. Okay, if two vessels were connected as in figure above, one vessel containing lithium bromide water solution and the other pure water, each liquid would exert a water vapor pressure. At equilibrium, water vapor pressure exerted by the two liquids would be equal. So that's the point you need to emphasize, that at this point here, at equilibrium, the water vapor pressure exerted by the two liquids would be equal. When it attains the equilibrium, it would be equal. But this equality can be achieved at different solution temperature and different concentration. Okay, I will try to explain you further when we look at the graph. When you look at the graph, you will understand that I can have the same pressure, same vapor pressure for different solution temperature and concentration. An example of one equilibrium condition is noted in this figure. So this is one of the example. So let's look at the chart and find out this 80 degree 59% at and 7.38 vapor pressure. Here's the graph. So if you look at this graph, on the right hand side, on this graph we call it PXT, from this side, from the right side. Px is the x-axis, Px, and T is this temperature, the solution temperature of pure water. So this is water temperature. Okay, so if the water temperature is 40 degrees centigrade right here, as you can see, right now we have this condition. We say the water temperature in our water tank is 40 degrees centigrade. So its vapor pressure on the right hand side will be 7.38. The vapor pressure is 7.38. So the other tank must have 7.38 pressure. So if 7.38 pressure is there, then if we know the temperature, we can measure the temperature of the solution, and we measured it, it says 80 degrees centigrade. So we draw a horizontal line from 7.38 to this solution line. This is the solution line. This is the solution temperature. These are the different solution temperature. Okay, so we draw a horizontal line from here till it crosses the temperature, the solution temperature of 80 degree. So the solution temperature of 80 degree. Okay, so from here we draw the line like this till it crosses the 80 degree line, 80 degree solution temperature line, and then we draw the vertical line from there, and in the axis along the x-axis it is the concentration of the solution. So it tells you lithium bromide in the solution by mass. So here it is like 59%, that's what it says. But you could have the same vapor pressure at a different solution temperature. Let's say if I go up to here, this is 70 degree solution. Here it is this 70 degree solution. Okay, this is the 70 degree solution, and 70 degree solution, vapor pressure is same. So then the percentage at 70 degrees solution will be 55%. Instead of 59%, 55%. So 55% of lithium bromide in water at 70 degrees centigrade will also give the same vapor pressure. So for the same pressure, we can have different combination of solution temperature and concentration. So that's what we mean by equilibrium. That it has to attain the equilibrium. If equilibrium will be attained where the pressure is same, but the solution could have a different temperature and different concentration. I hope you understand. So let's go back to our original screen where we were. Okay, here. So an example is 40 degree, saturation pressure will be 7.38. The same vapor pressure would be developed by lithium water solution at a concentration and temperature of 80 degrees centigrade. The concentration is 59% lithium bromide on a mass basis. Many other combination of temperature and concentration of solution also provide vapor pressure of 7.38. Okay, so let's move on to the second one. And now we find out what is the concentration. Now we want to use that concentration and solution temperature to find out what is the enthalpy. So that is figure number 17-5. 17-5 is the temperature, pressure, concentration. PXT diagram, no, it's previous figure. Concentration is the abscissa of the graph, and water vapor pressure could be considered the ordinate as shown on the vertical scale on the right. So as here, one side is the water temperature, the other side is the water vapor pressure, and x-axis is the concentration of lithium bromide, x. So PXT from right to left, PXT. Okay, so that's the diagram we discussed. Okay, for convenience, the saturation temperature of water, of pure water corresponding to these vapor pressure is shown on as the ordinate on the left. The chart applies to saturated condition where the solution is in equilibrium with the water vapor as in the vessel on the right in figure 17-4. So that is the figure, this figure here, 17-4. Okay, so that's the graph that I try to explain you. If you have any question on it, you can ask me. Now we want to go on this second situation. This is again the same 17-4 figure. Okay, just to remind you that this is what we are talking about. The pressure, temperature and concentration chosen as example in figure 17-4 can now be verified. Okay, now we can verify it from the chart. So if we have 40 degrees centigrade, 7.38 pressure and 80 degree solution temperature, then the concentration must be 59%. So that's what it means. We can verify. If the temperature of the pure water is 40 degree, the vapor pressure of the liquid exerts is 7.38 kilopascal, which can be determined from the opposite vertical scale in the in figure 17-5, the same figure. A lithium bromide water solution with a concentration of 59% and temperature of 80 degree can also develop a water vapor pressure of 7.38. If the solution had a concentration X of 54% and a temperature of 70 degrees centigrade, the water vapor pressure would likewise be still 7.38. That's the other example that I tried to explain you. Okay. Lithium bromide enthalpy of the lithium bromide solution. How to find out the enthalpy? In order to perform thermal calculation on the absorption refrigeration cycle, enthalpy data must be available for the working substance at all crucial position in the cycle. Water in the liquid or vapor form flows in and out of the condenser and evaporator. So enthalpies at these points can be determined from your table of water or steam table that we famously call. So from steam table, condenser and evaporator conditions at inlet and outlet can be determined. The 3 points that I showed you. So that can be determined from the steam table. Now it is for this solution which is in the absorber and the generator. How to find out the enthalpies there. So one part we covered, how to find out the concentration of lithium bromide in those container using the chart. For the enthalpy, we are going to use another diagram. In the generator and absorber, lithium bromide water solution exists, for which the enthalpy is a function of both the temperature of the solution and concentration. Figure 17-8 presents enthalpy data for lithium bromide water solution. So this is 17-8. So this one is giving you enthalpy on the left hand side. This is the diagram which we are calling HXT. So it is enthalpy, concentration and temperature. Temperature is the curves are drawn on the constant temperature. Okay, constant temperature, solution temperature. Okay, so this is a temperature of 150 degrees centigrade solution. This is the temperature of 140 degrees solution temperature. So going back. In figure 17-8 presents enthalpy data for lithium bromide water solution. The data are applicable to saturated or subcooled solutions and are based on this is the important thing, based on a zero enthalpy of liquid water at 0 degrees centigrade and zero enthalpy of solid lithium bromide at 25 degrees centigrade. So the charts has been developed, the enthalpy chart 17-8 has been developed by giving a zero enthalpy value to water at 0 degrees centigrade and zero enthalpy to solid lithium bromide at 25 degrees centigrade. So these are the datum lines which is considered. If you change this datum line, then we can consider this is 0 degree enthalpy, zero enthalpy at 0 degrees centigrade is also used in the steam table. So we don't want to change it, but this lithium bromide zero enthalpy at 25 degrees centigrade can be changed. Some other books have these similar charts, but their charts will look different because their datum line for the lithium bromide is different. That's why. So this is the Stoker's that we are talking about. Stoker is using 0 degree for water for 0 enthalpy and 25 degree for lithium bromide for 0 enthalpy. Okay. Since 0 enthalpy for water in the solution is the same as the conventional tables of properties of water, the water property tables can be used in conjunction with figure 17-8. So that's the criteria. Why do we use 0 enthalpy at 0 degree for water? Because our steam table is also generated using the same idea. So that's why we are trying to use it. But this lithium bromide is a new one. Okay. The enthalpy value shown in figure reference 4, this is the reference in your Stoker, okay, are based on a different datum plane for the solid lithium bromide. So lithium bromide datum can be changed from 25 degree to some others. In that case, your chart will be different, looking different, okay, and it will give you different values. But the end results of the calculations are essentially the same. The end result will be same. Even if you change the datum and you consider that datum, even then your overall enthalpies calculation will be same. Okay. So moving on, so this is that chart. If we know the solution temperature, okay, which we can measure, and if we know what is the concentration that we find out from the, if we know the solution temperature and if we know the concentration here from 17-5, then we can tell what is the enthalpy value. Okay, so with the help of those two information, we can get the enthalpy of the solution from the HXT diagram. All right, so moving on. Okay, so that's all about how to get the enthalpy. I'll try to do some example on it too, but that's all about the enthalpy, how to calculate the enthalpy for the solution and how to find out the enthalpy of the water. So next is to consider a modification in this. Next is to consider a modification in this cycle. The modification is to add a heat exchanger between the absorber and the generator. So here's the diagram. So we have added this heat exchanger, this one. We are trying, because we're trying to make it more efficient. So we're trying to save some energy, some heat. This is the heat exchanger mechanism which is being added. An examination of the simple absorption cycle and operating temperature shown in figure 17-6 reveals that the solution at point 1 leaves the absorber at a temperature of 30 degrees centigrade and must be heated to 100 degrees centigrade in the generator. So here the temperature which is leaving the absorber is at 30 degrees centigrade, and when it comes to the absorber it has to be heated to 100 degrees centigrade. And then again from this 100 degrees centigrade we are getting the solution back into the absorber, and then we are cooling it here in the absorber, either through the air or we supply cold water inside the absorber, cold water coil inside the absorber to cool it. So we are basically in the absorber we are trying to cool it, and in the generator we are supplying the heat. So there is a waste of heat. Here we are supplying that heat in the generator, and here we are trying to extract that heat, waste that heat. So to save that energy we are implementing a heat exchanger between the two. Similarly, the solution at point 2 leaves the generator at 100 degrees centigrade and must be cooled to 30 degrees centigrade. So whatever is leaving the generator is at 100 degrees centigrade, but when it comes to the when it comes into the absorber, it has to be cooled to 30 degrees temperature. So we must have to cool it down to 30 degrees centigrade. One of the major operating costs of the system is the heat added in the generator, and realistically there will be some cost associated with the removal of heat in the absorber. Okay, so of course when we are supplying heat here, so there will be at least some cost to that, and then we have to extract the heat from the absorber, so there will be some cost associated with that. So in order to save that amount, what we can do, we can apply the heat exchanger. A logical addition to the simple cycle is a heat exchanger as shown in the figure to transfer heat between the two streams of solution. This heat exchanger heats the cool solution from the absorber on its way to the generator and cools the solution returning from the generator to the absorber. So this heat exchanger, what will it do? It will, as the heat 30 degree solution is going through the pump into the generator, and the 100 degree solution is coming back from the generator to the absorber. In between these two pipes will transfer heat. There will be a heat exchange between these two. Okay, so there will be some saving. Instead of heating a 30 degree solution to 100 degrees centigrade, now we can save some energy, as because of the heat exchanger we only have to heat a 52 degree solution to 100 degree temperature. So that is the advantage of employing a heat exchanger between the generator and the absorber. So the high temperature solution can heat up the cold temperature solution to save some energy. So I would like to stop here. Then next one we will discuss the COP of the absolute. Then we will discuss the ideal absorption refrigeration system, COP of the ideal absorption refrigeration system, and then we'll do some example on it. So I hope you understand. This is a very simple cycle, and the calculation is also very simple. So we will do some example, and then if you do some practice on it, the practice problems are given in your handout. Then it will be fairly if you practice it, you will become an expert to solve the problem numerical on this cycle. Okay, I thank you all, and inshallah we will meet soon again.